Hello everyone, this is Mr. Secoder here. Today I am going to discuss an exciting problem from the Codeforces Round 596 Division 2 Problem E, which is rock is push. Let's look at a question first. You are at the top of left cell 1,1 of n by m matrix, you can say. Your goal is to get to the bottom right cell n, m. You can only move right or down one cell per step. Moving right from cell x, y takes you to the cell x, y plus 1, while moving down takes you to the cell x plus 1, y. Here, some cells of this matrix contains rocks. When you move to a cell with rock, the rock is pushed to the next cell in the direction you are moving. If the next cell contains a rock, it gets pushed further and so on. The matrix is surrounded by impenetrable walls. Thus, any move that would put you on any rock outside the matrix is illegal. Let's see what this question is saying. Let's say you are at this particular position x, y. Then you can only move to the one cell to the right or one cell to the bottom, but you can't move to the top or the left. So when you are here and you are moving from this cell to the right, then this rock is pushed to the right. If you are moving from this cell to the bottom, then this rock is pushed here, and since there exists another rock here, that gets pushed even down. So this rock is pushed down. So if you are here and then you are trying to push further to the down, you can't push this rock to the bottom because this rock here can't penetrate to this wall, because these walls are impenetrable. So you can't make a move from here to the bottom cell. So if you can see here, it is guaranteed that the starting cell, that is cell 1, 1, is empty. There exists no rock in any of the test case in that particular cell 1, 1. So the constraints are n and m are in between 1 and 2000. You need to count the number of different paths you can take from the start to the goal cell, that is from a starting cell here 1, 1 to the last cell here n, m. You need to find the number of different legal paths you can take from the start to the goal. Since the answer will be too big, you need to print the module answer modulo 10 power 9 plus 7. And two paths are considered different if there exists at least one cell that is visited in one path but not visited in other. Now if you look at this example here, there exist 4 such legal paths. How? This is a 4 such legal paths possible. If you are moving from the current cell starting from 1, 1 to the last cell n, n, these are the 4 legal paths that you can choose. So let's look at how to approach this problem. Before diving into the direct approach of this problem, we need to understand the concept of cumulative sum. Let's say let's consider there exists a rock here, and let's consider this. Now you need to find the number of spaces that exist from current cell to the last cell. You need to find all number of cells that are free without rocks from the current cell to the last cell. That too are with constant time, but you can take a space of big of n. How this is possible? You can use a cumulative sum here. Let's say I'm here at the current cell, and since there exists this, I can place 1 here. Since I'm here, I need to find the number of cells right next to it with empty spaces. I need to count the number of cells with empty spaces from here to the last. I can simply use the next cell right next to it, and I can increment the sum here. So this will be 2, which indicates that there exists 2 spaces from here. If I come here, since there exists a rock, we can't increment it further, so we'll use the same value here. Since there exists a space here, the number of spaces till now will increment. So here we have 3 such spaces from here till the end. Similarly here, since it's a rock, we can't increment it. Since it's a space, we can increment it. Now I can find, in any range, I can find the number of spaces present in that particular segment. Let's say I take this segment. If I need to find the number of spaces exist in this segment, I can simply subtract the number of spaces till here from the last and the number of spaces from here. So it will give the number of spaces exist here. It's nothing but 3 minus this 1, which gives you 2. So there exists 2 spaces here. I think the cumulative sum concept is clear. Okay, so we will use these cumulative sums 2 times in this problem. So let's look at the actual approach. Let's say you are here. We will break the original problem into 2 such problems. One is the number of ways that is possible by taking the step downwards and reaching the cell n, m, and the second subproblem is the number of ways that you can reach the cell n, m by moving rightwards. So if you combine these 2 problems, you will get the solution of reaching the last cell by taking either step downwards or step rightwards. So if you want to calculate the number of ways that you can reach the last cell by taking the step downwards, will be given by the number of ways you can move from here to the last cell by taking the step rightwards, plus the number of ways that you can move from here to the right and reaching the cell n, and the number of ways that you can reach here reach the last cell n by taking the right step here. If you sum these possible counts, you'll get the number of ways you can reach from current cell to the last cell by taking the steps downwards. Okay, similarly, if you are at this particular position and you want to reach the last cell by taking the step leftwards, you can either move from here to here, or you can either move to here and then here, or you can either move from here to here and then downwards. So this further breaks into sub problems where you are at the current cell and you want to reach the last cell n, m by taking the step downwards. Similarly here, by taking the step downwards, how many number of ways you can reach the cell n, m. Similarly here, this is nothing but a dynamic programming problem where you are using the sub problems. Let's look at another example of this from reaching this particular current cell to the last cell. Let's say you are here and you want to calculate the number of ways that you can move from here to the last cell by taking the step rightwards, because this is using in order to calculate the number of ways that you can move from here to the last by taking the downwards. Okay, since you are using this is a sub problem of calculating the top problem. So in order to calculate this, what you do is you move to the step left, and then this rock will be moved here, and then you can solve other sub problems moving downwards. Okay, I think the idea is clear. I'll explain it once again. Let's say you are here and you want to count number of ways you can reach the last cell by taking the step right is nothing but the number of ways that you can reach from this cell by taking down step to the and reaching the n+1 n, m cell, or you can move like this here and then you can move from here to the downwards, and then you are again solving the similar kind of sub problems. So the way of solving this is similar at every step. So you are utilizing the subproblems uh, left movement and right movement sums in order to reach the n cell n comma m, and you're processing the top cell that is behind the previous cell in order to calculate the subproblems of current cell. So if you're here, you can't move anything or anymore to the right. Okay, so when you're here, you need to find the number of spaces that exist from here to the right, so that you can only move those many steps to the right. So let's say you are here. Okay, you can only move 2 steps, because when you move for the first step, you will come here, and when you move for the second step to the right, and you will come here. So you can only move 2 steps. This is nothing but the number of space exists here. Okay, in this segment you will count the number of space exists, and you can only move those many steps, because after moving those many steps, you are at a position where you can't move further to the right, because the walls are impenetrable and the rocks can't penetrate through the walls. I think the idea is clear. So we can even use a cumulative sum here in order to calculate the suffix sums, where we need not iterate further. Let's say you are here, and you can move 2 steps to the right. Sorry, so you're here and you can move 2 steps to the right. Okay, so when you're here, and you can move here, and then you can find the subproblems by moving downwards, or you can plus the number of ways that you can reach from here by taking the step downwards and reaching the last cell. So these are the 2 suffix sums that you need to include, so that you can easily calculate the number of ways by taking, let's say you have all the suffix sums calculated. So if you want this suffix sum, you can simply remove from this suffix sum to this, so you'll get this segment sum. Okay, similarly you will do in the bottom by moving the bottom. That is, when you're in the current cell, you can actually move from here to here, or from here to the right. So this is nothing but you're again solving these subproblems and using those sum in a suffix sums. Okay, if you want to calculate the number of ways that you can reach from this particular cell to the cell n comma m, this is nothing but sum of these cells, sum of the highlighted cells, where each entry consists of the number of ways that you can move from current cell to the right, and reaching the n plus n comma m. Okay, the idea is clear. Here we even use the suffix sum here. So if you want the number of ways that you can reach from here by taking the step downwards, is nothing but the total segment sum minus the segment sum here. So you'll get this segment sum. Let's look at the code implementation. So I'm declaring a macro where right I set 1 and down I set 2, because I'm using a 3D matrix where the last dimension indicates whether you're moving to the right or moving to the down. So I take a dp which stores the possible ways that you can move from the current cell by taking either of the steps to the right or to the down and reaching the cell n comma m. It will store that particular count. So s will store, and moving down will be stored by the dimension 0, and the moving right will be stored by the dimension 1. Similarly, the suffix will store the number of possible ways that you can reach from the current cell to the right. All these suffixes will be stored here. Okay, So for that purpose we use s, and the count will store the number of spaces present from here. Let's say if you're here, the current cell will store the number of spaces that exist from last until the current cell. Okay, so here it contains 3, and here it contains 2. In this cell it contains number 2, and here it contains 3, and here it contains 4. That is stored in the dimension of, since you are moving right, it's stored in the dimension of 1. In the dimension 0, you want to move to the downward direction, so you store here you store for the dimension 0 you store the count of 1 here, because there exists only one space in this segment, and here you will store 2 because there exist 2 spaces in this segment, and you will store 3 here because there exist 3 spaces, and similarly 4 here. So I'm reading n and m, and matrix contains whether there exists a rock or space. If there exists a space, I'm using 1 there, and if there exists a rock, I'm placing there 0. You can see that here. If the current cell contains space, you are storing 1. If not, if contains rock, you are storing 0. And here I'm calculating the cumulative sum that I said. Let's say I'm actually iterating over the rows here and calculating the cumulative sum that is possible by moving rightwards. I mean, if you're I'm moving the row wise, and in each row I'm moving from the right to the left and calculating number of spaces present in the segment till this cell. Okay, and I'm storing in the dimension of right. That is, in the dimension 1 I'm storing these rows cumulative sum, and again I'm moving in the column wise and storing the cumulative sum from bottom, that is number of sums that exist, number of spaces that exist from last cell to the current cell in that particular column. Let's say in this segment, in this current element, it will store 1 because there exists one space in this segment till the last element. From in this current cell, it will store 2 because there exist 2 spaces in this segment. Here it will store 3 because there exist 3 spaces. Similarly, here it will store 4 because there exist 4 spaces. So I iterating from column wise, and for every row I'm calculating cumulatively the sum I'm storing in a dimension of down. Okay, because we are interested in the segments column wise. And now if the matrix contains a rock at the last cell, we can't move to the last cell, because if there exists a rock here, even though you move to the surrounding cells, you can't move to that cell because these rock can't penetrate to the walls. Okay, you can't move from the top to bottom, or you can't move from this cell to the right. So this is there is no way to reach the last cell, so you output 0. If there is only one cell and there is no rock there, because if there exists a rock, we already solved that sub problem. So the only problem is there exists a one dimension matrix, and there exists a space we went 1. So here we are storing 1 at the last cell, moving downwards or moving to the right. Similarly, in the suffix sums, we actually store 1 in the for the last cell, that is n comma m. So we are moving from the last cell to the top cells, because let's say you are here, you're using the sub problems of moving right from here, or moving right from here, or moving right from here. You're using those sub problems, so you need to in order to use those sub problems should already be pre-computed before. So we are moving from the last cell topwards, so that the subproblems of bottom cells will already be calculated, so you will use those subproblems. If you are here and if you want the count of number of spaces exist from current cell to the bottom cell column wise, that will be given by this particular dimension and this particular index, because these are already calculated on the top. Okay, similarly you can get the number of spaces existed in row wise using right, as you can get here. And the DP problem is a problem of moving downwards and reaching end from the current cell will be given by the suffix sums that possible. I mean, if you're here and you want to count the number of ways that you can reach the last cell by moving the downwards, will be given by the suffix sums that is possible. What do you mean by this? Because you are actually summing this number of ways and this number of ways moving from the current cell to the right and reaching the last segment. So you want all these sums till the number of spaces existed. So you are actually calculating these suffix sums are already calculated after iterating the below cells. So you just need to use the cumulative trick that I showed before, and you need to calculate the number of the sum of this cumulative. I mean, if you want to calculate all this sum, you can simply from this sum you can actually remove this, so that you will get this. That's what we are doing here. Similarly in the row wise. So, and for to use these suffix sums for further top problems, we actually store in a suffix sums. So let's say you already calculated the suffix sum of this. Okay, now you need to calculate this and add to the previous one. Okay, that's what we are doing here. Similarly in the moving rightward direction. So at last you will have a solution by adding the from the cell 1, 1 moving rightwards and reaching the cell n, n, and moving downwards and reaching the cell n, m. So let's look at some test cases and test them for our solution. I already compiled this, so let's see here. Sorry, yeah, we got a solution, 4 different paths as desired. So thank you for watching. Subscribe and hit that bell icon to get notifications whenever I upload a video. Thank you all.